Let's do another example of solving limits algebraically. In this one, notice that we are trying to solve the limit as x approaches 0 of a rational function x squared plus 9x plus 20 divided by x plus 4. And so another limit law that we have not yet used in any examples is number 5, which says the limit as x approaches a of a function divided by another function is equal to the limit of the numerator divided by the limit of the denominator separately, provided that the denominator is not 0. So this is an important note that was not printed on our packet, but will be in your book. But all of that being said is that if you are to use the limit law where you're going to take the limit of the top and the bottom separately, you cannot do it if the bottom will result in 0. That is not allowed. So in this first case, notice that's not the case, because if we do separate the limit to the top and the bottom, we get the limit as x approaches 0 of x squared plus 9x plus 20 divided by the limit as x approaches 0 of x plus 4. And both of those limits, the limit on the denominator would actually be 4, which is why we're allowed to do that. Notice for the example below it, if we were to plug in -4 into x plus 4, that would be 0. And so this would not be allowed in this case. So the question is, how would we approach this limit in the case where we cannot use the limit law? Where this would be an example where we can't do it algebraically, or actually you can, but there's another strategy. Let's get to that in a second. But anyways, so the question is, well, where do we go next? Well, like in the previous example, one of the takeaways was that if we have a polynomial, we can simply split it down and take the limit of each x individually. But TLDR, you can just plug in 0 in to any polynomial function within a limit, because limits will break down across addition. Basically, it will turn into the limit of this plus the limit of this plus the limit of this. The 9 will pass through, the square will pass out of limit, and what we're going to get is limit of x, which is 0, plus 9 times the limit of x, which is also 0. It's going to boil down to plugging it in. So what I'm saying here is we are just allowed to plug it in. So we're going to get 0 squared plus 9 times 0 plus 20 divided by 0 plus 4. And same goes for the bottom, kind of like in this example, well, where TLDR, we just plugged in -5 in for x. And what that amounts to is, 20 over 4, which is equal to 5. And we can solve our limit by, sometimes I might refer to this as direct substitution, because at the end of the day, all I really did was I took 0, plugged it in to both of the polynomials, and solved. But the whole point here is that will not work in this example, because limit law 5 is not valid if the denominator is 0. So again, the question becomes, well, in this case, what do I do instead? But that's where with polynomials, we have another tactic that can sometimes help us solve this limit, which is by factoring. And it turns out that if we factor these polynomials, we can simplify and solve the limit from there. And again, this would go under the algebraic strategy, because we're using algebra to try to simplify this particular limit. Technically, you could have factored here to solve this too, but what I wanted you to notice is that we didn't really need to factor it because this limit was perfectly well defined on the denominator. This one is undefined at -4, which again, because you can't divide by 0 in mathematics, we are not allowed to simply plug it in. And question mark is not an acceptable answer either, of course. But so if we were to factor the numerator, we'll notice that x squared plus 9x plus 20, if we're using the guess and check method of factoring, we have to have x times x to make x squared, but then to make 20, the other two terms of our binomials must make 20. So there's a couple options. It could be 1 and 20, 2 and 10, but 4 and 5. Also, the inner products must add up to 9. So just to review a little bit of algebra here, since 4 and 5 add up to 9, this will give me x squared plus 5x plus 4x, which make 9x plus 20. And that is the correct way to factor the polynomial on the top. Now on the bottom, x plus 4, that can't be factored in any meaningful way. And what you'll notice is that we have a common factor in the numerator and denominator. Now, generally speaking, those two cannot simply be canceled because of one specific value, but within a limit, the reason that we're allowed to actually cancel out x plus 4 like so is because we're not looking at it at -4. So one of the primary, and not to get overly into the technical side of the math here, is that these expressions are not directly equal to one another, even though in algebra class, a lot of times teachers will say, well, in this polynomial, you can simply cancel out the common factors. That's not entirely true because x plus 5 is not equal to this expression at specifically -4, because that's where the original expression, x plus 4, would be undefined, would be divided by 0, whereas x plus 5, that is well defined at -4. And so essentially there's a problem with this cancellation specifically at the value of the 0. But the reason why within a limit we actually are allowed to cancel this is because the limit as x approaches -4 is always assuming we're not actually at -4. We're looking at what happens as we're close, and it will be well defined nearby -4. And if that doesn't make sense, it's not really a big deal, because at the end of the day, you can factor it, you can cancel it out. Limits get around that algebraic technicality. And so what we're left with here, and why this is such a helpful tactic, is we're left with the limit as x approaches -4 of just x plus 5. And this is well defined. This is just something where, again, like the previous example, I can take the limit of each individually. Limit of x is just going to be -4, and the limit of 5 is just 5. And so what I end up with is 1, the value of this limit as x approaches -4 in there. And so circling back to summarize, the reason we could not evaluate this immediately is because the denominator was undefined. But if we can factor and cancel common factors, then we might be able to evaluate the limits after doing so. Technically, this does not always work either. Sometimes you still might run into limits that you can't solve, and that's why it's always nice to have a numerical or graphical approach in your wheelhouse. So one thing we could always do in this case is let's check our answers. So if we graph this rational function in our calculator, so we have x squared plus 9x plus 20, and make sure you use parentheses around the top and bottom of a rational function, because what a fraction bar always implied is it's this whole thing divided by this whole thing, ignoring the standard order of operations. And that's, there's always an implied parentheses around a fraction bar such as this. But if we go ahead and graph this function, what we can see is, it actually just looks like a straight line, which is kind of funny. But if we trace it towards 0, so if you hit this trace button and you just press 0, what will happen is you can get your cursor exactly to a point. Notice that, at 0, this function just evaluates to 5, and it's clear that the limit is continuous on both sides. Well, I have not defined what continuous means, but we'll talk about that and why that's related to limits soon in the next videos. Now, if we say go to -4, I'm going to go ahead and trace to -4. What you'll notice is there's actually a problem, because as I was saying, this function is undefined at -4. So on the graph, notice how it doesn't do anything. There's no more trace. But if I move a little bit to the left, notice that I have -4.2 and so on. I can actually approach -4 from the left-hand side. And as I get really close to -4, notice that the value of limit, I can't quite tell exactly, but it does appear to be approaching 1. And similarly from the right-hand side, if we get close to -4 coming back this way, it's very close to 1. We can't get exactly on -4 because it's undefined, right? The problem with -4 is that would give us something divided by 0, and in math, dividing by 0 is always undefined. But you could even say, plug in, what about 3.999? Because, right, when the limit is going towards -4, that means we're getting arbitrarily close to that value. So you can get as close as you want and see that if we get really, 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 really close to -4, we get really, really, really close to 1. And we can come up with the same conclusion, yet that, the limit of this as we get close to -4 is 1. But my whole point here is plugging in -4 does not work, because that gives us an undefined value, and we do not know what that limit would be. Because what actually it's going to give you is 0 over 0. And so don't actually write this in your notes, because that is what's called an indeterminate form in math. That's something that is, you might say, well, any number divided by itself is 1, which we do end up getting here. But actually, that's just a coincidence, because if you have 0 divided by 0, that actually could be anything. It could be infinity. It could be 0. It could be a negative number. It's really, it's not a defined thing. And really, the source is because dividing by 0. This is a nonsensical mathematical operation. You can't divide into 0 groups. It's just not allowed in math. And that's one of the main problems with certain functions, is when you're dividing by 0, you get a problem. And limits help us rectify that problem to say, well, what happens if we get close to the value? Since at -4, it's undefined. But if we get close, what happens? And we can tell that as we get close to -4, we get close to 1. And yeah, that's it for this video.